Hi guys, and welcome to this webinar. Thank you for joining us. The webinar is on electrical machines and how you can use our electrical machines to teach transformers in particular. For this specific webinar, I will ask you if you want to just chat and ask questions as we go, then that is absolutely no problem. So please unmute yourself and feel free to chip in at any time. We want it to be a bit more of a conversation than our normal webinars. So at any point, please do unmute yourself and ask questions as we go. Alternatively, if you don't have a microphone or if you would rather just post something in the chat, we do have someone at Matrix who's looking at the chat throughout the webinar. I have today with me John, who will be helping me with some of the more difficult points. So yeah, let's get started. I'm just going to share my screen with you initially and show you a short video. And if you've got any questions as we go, please just shout out. Cheers. Thanks for watching that, guys. The follow-up to this webinar, I will send a link to that video as well if you want to share it with colleagues. I'm now going to share my screen again, and I'm going to show a short presentation. Give me a second. I'm going to pass you over to my colleague, John. Enjoy. Thank you.
Okay, this discussion, if you like, is all about electrical machines with transformers. And I was just explaining to Al, the word electrical machines is a bit confusing really, because transformers are included in electrical machines as far as electronic engineers are concerned. So normally electrical machines, or very often people think of it as actually being motors and generators, but transformers are definitely an electrical machine. So today we're going to look at our electrical machines kit. Some of you may have seen this, some may not. We're going to show you roughly how this works. And then we're going to move on and look at the transformer parts of that. So with electrical machines, this is modern electrical machines. There are 4 different curriculum packs that go with it. We just explained to Joshua a few minutes ago that the idea behind this equipment is that it can be used with different types of students. So we start with students of electrical installation, and they need to understand the wiring of electrical machines and the different characteristics. Then we go on to the core course, which is what we call a level 3 course. And a level 3 is equivalent in terms of the academic learning objectives as to what you would find in a high school at the age of 18 with a traditional sort of academic subject. So that's level 3. And that's all about the electrical machines, the characteristics, some of the mathematics behind it, how they behave, how they're wired, how they're constructed, things like that. After that, we then look at a typical university second year course on how to use electrical machines with Matlab. And then after that, we go on to another second year course, second year university course, which is looking at electrical machines from quite an academic point of view. And that's what we're going to be looking at today. So this is a level 5 course that we're looking at. For those of you who are from UK colleges, this is equivalent to a BTEC HND. And in particular, what we're looking at is, I believe it's unit 45. There's 2 units actually there, but unit 45 is our core. So this electrical machines kit, you can see it there on the bottom right. What we've done is we've shrunk the traditional electrical machines kits that you might have seen available from other companies. And in this shrinking, using 24 volts, the huge advantage is that we can now fit all of the electronic instrumentation and power supplies into one small desktop box. And that's that black control box you can see there. And it's an incredibly sophisticated box. It's got about 4 computers all talking to each other, communicating back to a PC via the USB lead. And it comes with 6 different software applications that you can use it, so you can use it in different ways. So it's an incredibly sophisticated set of machines, but it's also quite low cost. I've just probably said most of this. So it's also very safe. There are no moving parts that can be touched by students. 24 volts AC/DC. You can use it manually without a PC, or you can use a PC with it. There are 16 different instruments for measuring voltage and currents in there. It can all be stowed away easily because the machines are relatively small. Here's the box itself, and it's DC, single phase AC, and 3-phase. Lots of virtual instrumentation. There's a load for a dynamometer. There's a start run capacitor for understanding single phase induction machines and how they're wired. 16 instruments. It comes also with a full API. That's an application programming interface. And that means it can be used by bits of software like Matlab as a slave. So Matlab can do the turning on and off of all the inputs and outputs, and can also take the measurements. So it can be operated entirely from Matlab or LabVIEW, and it's small. This shows you some of the machines that are available, left to right from the top. There's a dynamometer, and a dynamometer is basically just a DC motor with an encoder on the shaft so we can measure its speed. And it connects to the box, and we provide a varying resistance on the 2 terminals so that we can adjust the load. And basically, it's a computer programmable load, but it happens to be a DC motor as well. So it behaves like a dynamo. It generates DC. Then we've got another DC motor that can be plugged onto the dynamometer, and the DC motor slides on those two aluminium rails and mates nicely with the coupling on the dynamometer beneath that plastic tube to keep all the moving parts away from the students. There's a universal motor, which is basically a DC machine. It can be used with AC. Its performance isn't as good. So that works with both AC and DC. Then there's a single phase induction motor, a shunt motor, again a DC machine, a three-phase induction motor, and the last one is a brushless DC motor. Now, this is a very modern machine. The power of that very small unit you see there is the same as the power of all the others. It requires quite a bit of driving in terms of the it has to be driven by a computer rather than just a voltage. But just looking at that, you can see why the brushless DC motor is taking over huge numbers of applications, just because it's smaller, lighter, and it's the same power as all those other machines you can see there. So this is modern electrical machines. We've taken a decision that the brushless motor has to be in there. We haven't included things like compound motors. They are in curriculums, but they're pretty small in terms of their usage in industry.
Just had a question about VFD within the control box.
It is a VFB system. So I think VFD stands for variable frequency drive, and the machine that the box creates for the induction motors, it creates a frequency between something like 30 hertz and 100 hertz, which is exactly how VFDs in industry works. So again, it's modern electrical machines, and actually we're driving this with a digital signal at all times. One of the other reasons why we're able to shrink this down is that we are not using traditional Class B amplifiers and sort of transformers in there. It's a very modern system. It requires quite a lot of silicon and quite a lot of intelligence. It doesn't rely on the traditional circuits that you find or found maybe 50 or 70 years ago. Okay, as I said, there are actually, there's an error there. There are 6 applications that this comes with. So this is a screen grab of a the three-phase induction control software. And you can see that you can vary the frequency of the output there. There are voltmeters and ammeters for all of the 3 different outputs, U, V, and W. You can see the dynamometer power, the dynamometer load, you can see the speed, and you can see the torque that is generated in the dynamometer. There's a couple of spare inputs on the box, so you can measure voltage and current there. Now, built in to this software is an onboard oscilloscope. And in this particular bit of software, it's an oscilloscope. In other bits of software, what you see there is a logging graph that will show you the speed torque characteristics of the motor when you set it up, right? That oscilloscope is fairly low bandwidth. It's there to allow you to see the phase difference between the voltage and the current. If you want to see the pulse width modulated output, you will need to use a faster external oscilloscope, but that's very simple to do with this package. So that gives you a picture of the quality and functionality of the software that's available to you. As I said, there are 5 other software applications, and we have different applications for different types of machine. So some of the DC machines have their own software application. The single phase and the 3-phase have their own application. You can see the details of all of these on the curriculum, and Al is going to give you a link to some of the curriculum so you can see those screens yourself later. Okay, now we've covered that. That's just another screen there showing the 4 different workbooks. All those workbooks are free of charge. You can download them from our website. And as educators, that will give you a really clear idea of the learning outcomes for this piece of equipment. Just a closer look then. This is some screenshots of the topic we're discussing today, which is this level 5 course, second year university. And this is all about equivalent circuits. We're going to go into a bit more detail there, but you've got 3 images there where you can see we're discussing with the students the equivalent circuit and what the terms mean. Here, this is a transformer. This is an experiment on a locked rotor for induction machine. This diagram tells the students how to set it up and these instructions. And this, on the right-hand side there, is a typical Matlab script that you might use to do some modeling. Now, for those of you from the UK, again, going back to unit 45, I believe it is, the unit there does specify Matlab or the equivalent. And a good tip for you there is a fantastic package called GNU Octave, which is a free mathematical modeling package, and it will do everything that you need. So you should take a look at that. And that's actually what we've used to do a lot of this work. We do have a copy of Matlab, but we have used GNU Octave just because it's a bit more accessible. So take a look at that. This particular course is going to take a student typically 15 to 20 hours to complete. The way we tend to work is that most of the sort of units, if you like, in British education tend to be about 60 hours. We know they're not going to do practical work for the whole of that 60 hours. Around 15 to 20 hours is probably appropriate in terms of working. Okay, this is the second one. This is all about Matlab and electrical machines. So that is where Matlab will be taking over the box. So rather than use our software and get the results and then build a model into Matlab with those results, this is working the other way around, where you're using Matlab to actually control the box as well. Okay. With this particular unit, you are able to use it on USB, but you're also able to use it through IP. So you can connect it to your network, or you can connect it to the internet. And if you wanted to, in these COVID times, you could set up a number of these bits of equipment, and the students could access them from home and could do all the work from home. Okay, I think we've covered some of this. At this particular unit, we're looking at transformer equivalents, induction motor equivalent circuits. We're going to gather the circuit terms experimentally. We're going to do some calculations, and then we're going to model those circuits. And we're going to compare the model that is generated from Matlab in terms of the performance with the actual results, and we're going to understand what the differences are. And we're looking at electrical engineering undergraduates and BTEC National 43 and 45. So the add-on kit for transformers, can we just move to a real camera, Al?
Yes, give me a moment.
Okay, so we've got a camera here. Where have we gone? Where have we gone? If you just come and hold that, Al. We're in our conference room here at Matrix, and you can see we've got the electrical machines box there, the control box. It's connected to my PC via USB. We're not going to use that today, but that's a dynamometer and the motor. And here's a little kit, which is a transformers kit. So basically what I've got is I've got a couple of cores there. This one here is 600 turns. This one is 400 and 600 turns. You basically slip them over an iron core like that, put the top on, then you screw the lid down like that, and we've now created a very basic transformer. Now the idea is that what you can do is you can then change the turns ratio, so you can build a model, you can compare the performance of the model with the real results, and then you can change the transformer core and check that your predictions are valid. So basically the box, this is the single phase output, and what we do is we just wire that to the primary, which is 400 turns, and then we are ready to go. Okay, can we go back to sharing my screen?
Yes, you just click at the bottom
There. Okay. What I'm going to do is quickly gather some results. Now, how can I? Okay, so you should be able to see now some software. And this is a single phase motor control software, but it's basically just a single phase signal generator at this point. So what I can do is I can put it on, say, 24 volts. I can run it. Now, I don't know if you can hear that, but there's a nice buzzing sound coming from our transformer. And I'm at 24 volts, 50 hertz. There's no dynamometer plugged in here, so that's not going to do anything. And I can capture the waveform. What I've got is I can capture about 6 or 7 different traces at once. But what I've done now, hopefully you can see that, is I've captured the voltage and the current. And there's not a lot of current flowing. And there's a bit of distortion at the top. So what we can do, rather than 24 volts, we'll go down to 16 volts and we'll just do that again. Okay.
You'll have to do that again. It put a different screen up.
Ah, okay. I apologize for that. Somebody pointed out I've got a different screen up. So I'll just start that one again. We've got it says here single phase motor control. It's really using the box as a single phase AC generator. And here's the frequency. I've got a voltage of 16 volts coming out. And you can see the current's 0.1 amps, 11.4 volts. And I've got an oscilloscope up here. And this is going to allow me to measure the phase difference between these waveforms. What I'll do is I'll just put a short circuit on the secondary, and I'll capture that waveform again. You can see the current's gone up to 0.9 of an amp now at 11.4 volts. And so this just shows you how the software works with regards to gathering the information we need. So we can see the voltage, we can see the current, and I don't know if you can see that on your screen, but when I put the mouse over the waveform, it says that at that point in X, we've got 458 degrees. The display is in degrees there. So the peak current is at 458. The peak voltage is about 398. So we've got 50 to 60 degrees phase shift between the two waveforms there.
I've got a question.
Okay.
How many types of transformer can we test?
Well, the kit comes at the moment with about 6 different cores. So I don't know how many combinations that gives you, but it gives you quite a lot of combinations. I think though we're going to cut that down. It's probably to only about 3 cores because of the voltage it generates. So with 3 cores, let's say you've got 200 turns, 400 turns, and 600 turns. I don't know how many transformers that is, 6, something like that. So certainly for the purposes of modeling and checking the models, there's enough there. So that shows you hopefully how the software works. Oh, screen share has stopped.
Okay.
Can we go back and let's go back to this presentation. Okay. Just going back to electrical machines, these graphs here show you some of the speed torque curves that you're going to be able to get with the electrical machines rig. And here you can see some typical oscillograms. Here we've got some phase angle plots between a single phase and 3-phase induction motors. Okay. So we've done that. So what we're doing here then is, with students, is we need to build an equivalent circuit. And if you look through textbooks, there are a few equivalent circuits, but they generally simplify to this equivalent circuit that you can see on the left. Can everybody see that, Al? Can you see that okay?
Perfect. We have had a quick question. I don't know if it's
okay.
Is it compatible with the first version of electrical machines? Pretty sure it is.
Yeah, is it compatible with first version electrical machines? Yes, it is. No problem there.
And another question, can we measure the power factor?
Yes, you can. If you can measure the phase difference between the voltage and the current, you can automatically measure the power factor.
Superb.
Right? In fact, that is the definition of power factor as I understand it. I think.
Hey.
Okay.
By who?
Okay, so this is our equivalent circuit. Let's just go through some terms here. This is the resistance of the primary, that's the reactance of the primary, that's the reactance of the secondary, that's the resistance of the secondary, and this is an equivalent model of the magnetizing reactance of the transformer, where basically the magnetizing reactance alters the voltage and current waveforms and also absorbs energy. So the energy loss, if you like, is modeled by that resistor value. Now, what we want to do in electrical engineering is we want to make a model of a transformer so we can then alter the physical model or physical transformer and then be able to predict without actually connecting this transformer into a circuit. We want to be able to predict how it's going to affect the behavior of the circuit. And to do this, what we want to do is we want to be able to take a transformer and we want to be able to gather the terms to make the model. And we do this with two tests. The first test is called an open circuit test. And basically what I'm going to do there, or what I've done, I'm going to inject a AC signal. There's going to be no secondary current because the secondary is going to be open circuit. And experience tells me that when I do that, the values of R1, X1, X2, R2 are relatively small compared to XM and RM. So I'm going to make the assumption that the circuit simplifies to this circuit you can see on the right. So if we inject a signal and we assume it's this circuit, by measuring the voltage and current and the phase between the two, we can calculate the values of XM and RM. Now, similarly, if I short circuit a secondary and a lot of current flows, suddenly the magnetizing losses and the effect on the phase of XM, if you like, becomes really small. And so the circuit simplifies to the one you can see here. So if I do the same mathematics, I measure the voltage, the current, and the phase between the two of them, then I can come to an understanding of what those values are. So what we do is we connect the system like this. So here's our transformer. This is the single phase generator, and we've got it plugged into an external voltmeter there, although a voltmeter on the box, if you like. And this allows us to measure the voltage and current. Now, in terms of how the students then do this, in the worksheet, you can see that they make the measurements, and then there's a sequence of mathematics that takes them through the steps involved to come up with the answers for these two components. Now, as you saw before, on the oscillogram, we can measure the phase just by putting our mouse on the top of the voltage and the top of the current, and making a note of the two angles, because the graph gives an angle in degrees, and that gives us a result. Now, when we do this, here's some results that we took on the 2nd of July. The number of primary turns was 400, the number of secondary turns was 600. The ratio there is 0.67 to 1. We measured the value of R2 just with a straightforward multimeter at 5.3 ohms. And then this shows the sequence of calculations that is carried out to get to those values. So we've got the frequency, the current, the voltage. We know the phase shift in degrees. We know the phase shift, therefore, in radians. We know that the reactance is VP over IP. So we know that that is 44 ohms. We know the angle between them, so we can determine the real and imaginary parts of that. So we can come up with a value for the real current, and then we can calculate the other values in the circuit. Any questions on that? because that's quite a tricky one. I've got a copy of the Excel spreadsheet and I can look at the maths in more detail if you like. But as academics, I'm kind of expecting that you know more about that process than I do.
There is a question, but it's not necessarily about this. Is it possible to test a three-phase transformer?
Is it possible to test a three-phase transformer? You know, the answer to that is yes, if you have one. We don't have a three-phase transformer. It's kind of on our list of things to have, though, but we don't have one today. But if you do have one, or if you have the facilities to make one, then the answer should be yes, you've got a three-phase signal generator effectively, and that shouldn't be a problem for you. Anything else?
Nothing yet, no.
Okay. So that was the open circuit test. Now the short circuit test is exactly the same. We just happen to short circuit the secondary. And the calculations are also exactly the same. Or the steps in the calculation are exactly the same. So we repeat the process with the short circuit test. Again, we repeat the phase measuring process between voltage and current. We make some assumptions then. We make an assumption that X1 is the same as X2. And we use a multimeter to measure R2. And then we come up with a value for X1 and X2. Now I've put ohms there. You can convert that to Henrys easily enough if you want to. So when you do that for this particular transformer, you come up with these values. Now, if you go back to the start of this presentation, we said that what you do is make an assumption that XM and RM are quite large compared to those other values. And you can see that that assumption is pretty true.
I've had another question, John.
Okay.
Is it possible to create a fault?
Is it possible to create a fault? I guess it is. You just short circuit something. Now, in this case, somebody,
1 second.
¿Estás hablando conmigo? Sí. ¿Qué me decías? ¿Qué está complicado? ¿El logo?
Hello. Okay, so yeah, you can create a fault. What we're doing here is short circuiting the secondary. If you like, that could be seen to be a bit of a fault, but this box you can do whatever you like with. If you short circuit the outputs of the control box, they will shut down. There's quite a lot of sort of different types of protection in the box, so you should not be able to break this box. Okay. I think from this point, there's a very good reason for modeling a transformer before you move on to modeling an electrical machine. So this next circuit you can see here is the circuit model for an electrical machine. And you can see that it's very close to that of a transformer. It's just got a second resistor in the secondary circuit, if you like. And that resistor is a term that's associated with the slip of the induction motor. And you can see the definition there is that's the equivalent. So it's based on R2, but it varies depending on the amount of slip. Now again, what we can do is we can do a free running test and we can do a locked rotor test. And that allows us then to make some assumptions about the relative values of these components in the circuit. And then we can deduce a model for the induction motor. Now for that, we have an add-on called the locked rotor add-on. And this basically is just a three-phase induction motor. And you are able to either get the rotor to be free running or to be physically clamped down. It plugs into the box, the control box. It allows you to measure the voltages and currents in those two circumstances and the phase, so that you can then come up with a model for what the equivalent circuit is. And in this case, you can see the mathematics there. and you can see the values that we've come up with for the components in the circuits. And then students can model that in Matlab or something else. Just to go on and look at that then, is my screen still being shared, Al?
No, it seems to have dropped off. 1 second. Is it this one you want to?
Yeah, yeah. That one, yeah. Okay, so this is a file that we keep that just shows all the different results and things that you can look at with the electrical machines. So here you can see we're looking at the PWM. That's a really interesting signal actually, because this shows you how we build the sine wave. We're basically across a sinusoidal half cycle. We adjust the pulse width modulation of the output so that it builds a sine wave, and then that is filtered out by the inductance of the electrical machine itself. So you can use an oscilloscope to see how that's done, and this is how VFDs work, variable frequency drives. Those are some of the results we've seen there, and it's this one I want to show you really. This is a graph that shows you with the equivalent circuit what the output ideally would be when it's simulated, and actually what the output we've managed to get through experimental data. So it would be very rare if you were to get these two to marry exactly, because there's always losses and things that you haven't factored in, but you can see that's what you're aiming for. Okay. Now I think I'm finished really, Al. I just wonder if anybody else has any questions. Or I tell you what I'd like to know from you guys is how you are going to deliver this kind of course, particularly for that higher national. So there's anybody out there who's going to deliver higher national unit 43 and 45. We think this is what you need to do for those 2 units. That's our interpretation of what the examination board want you to do. It'd be really interesting to hear if people think that's true, or if people have different ideas on how to deliver those units, or if they think this is appropriate.
Any comments or discussion about that particular unit that John's talking about, is unit 45? If you've got any comments, please post them now, or if you could unmute yourself, then that would be fantastic. Alternatively, if there's any questions about anything, now is a good time. We're all ears. I'm going to give it another minute or so, guys, just in case anybody does have any questions. Like I say, now is the time. If you've got any questions about electrical machines or electrical machines with transformers, or if you've got any queries about that particular unit 45, or any other unit where you think that electrical machines or transformers may be useful or appropriate, now's the time, guys. I'm going to give it a minute to 2 minutes. And if you've got any questions, that will be, now's the time. I will be sending a recording of this webinar to the guys that signed up. I'll also be sending the curriculum and the video for the electrical machines. So any questions, guys, before I end the webinar, now's the time. Before we end the webinar, and with any last questions, just a quick thanks to the people that have tuned in today. If you do have any questions that you don't ask now but have in the future or after the webinar, then please do send them to myself. You'll all have my email address by now. Any questions?
Yeah, we've got one here. Somebody says, will it be useful for the BSc program? Absolutely. This is undergraduate second year.
So yes, absolutely. This is undergraduate second year, so absolutely it is relevant for a BSc program. Thank you for the question. Any more questions before we end the webinar, guys? I'll give it another minute or so. Like I say, I will send you the recording of the webinar and the video and the curriculum. If there are questions that are prompted after, you know, myself and John will be happy to answer them. So please do send us an email. No, I think if there's nothing within the next 30 seconds, I will end the webinar. But thank you all for tuning in. I appreciate some people who are around the world have probably woken up and the first thing they've done is to tune in. So we appreciate that. Like I say, I'll send you the recording of the webinar, and with no further questions, thank you for joining us, and we will be in touch soon. Speak soon. Thank you.